Welcome to lecture 6 of MCS 472, to this pre-recording of a lecture on industrial mathematics and computation. So we started the course with statistical reasoning. In the next 2 weeks, we are going more into the engineering type of mathematics, and in particular the signal processing world. Many, if not most, engineers will regard industrial mathematics as engineering, and that is fine. We will, in this course, see that with the mathematics that we know, we can solve problems as well. So let us look at the first problem. So that's a problem to motivate and a little bit to guide this lecture. So we have a train that leaves empty, and there are a number of stations. In every station, on average, there are about 40 people mounting, and about 20% of the riders, they will leave the train. So suppose that we have to consult a train company, and a train company, given these data, wants to know how long the train should be. So we had the problem with the overbooking strategy in an airline. You could also rephrase this: in every station, is it okay that there will be 40 tickets sold? Or if you have 40 tickets, 40 people who expect to board the train, can you accommodate them? So the purpose is in this lecture not to question these numbers, but mainly take the data that we have and find a model with this. We can already solve this, so we can already use Monte Carlo for this problem, but in this lecture we will see this differently. So let's see how linear recursions arise. So the setup is that we have some process. There is a sensor attached to this. The data that comes from the sensor is analog and gets converted into a digital format and then given on input to the computer. So for this lecture here, we actually are going to assume that we are already having our input numbers, our data, given to us to the computer. The computer will manipulate, store, and display the data. So in a way, it's a summary of what was the setup of, say, a previous lecture on analyzing data. Okay, so this is called data acquisition system. So what comes in is a sequence of data, and last lecture also hinted why series is in some settings a natural word for one-dimensional data. And this will become clear with the z-transform of a signal. If we capture a signal, so we do some measurements. So if you think about temperatures, it can be every day, every morning, or it could be, if we look at the averages of the monthly temperatures that we did last time, the time unit can be a month. But it can also be quite shorter. So think about measuring speed, so where we have a measurement coming in over time. So we look at the signal in the time domain, and then we will define with these numbers a series, a Lagrange series, written here. So Lagrange means that the powers of the z are negative, as this will be very convenient, as will become later clear. So for now, this is the formal and somewhat artificial definition of what we will call the z transform of the signal. It will turn out that this z transform will capture some of the essential characteristics in a signal, which I hope will become clear by the examples that are coming next. So we have a mathematical model. So we are now actually turning things around. We are looking at a series and we're going to try to figure out what is the signal that corresponds to this. So let's start to look at some series. So here is a very simple series, so which you can reconstruct if you look at the factorization of 1 minus z to some power. Then you will see that the 1 minus z factors out, and what comes then in the quotient are the sums of the powers of z. Now, instead of taking one fixed power, one lets the power go to infinity. And one has the simplest series possible. If we put this series into into the format of the z transform, so instead of having powers of z, we are dividing by larger and larger powers of z. And now it turns out that this series then corresponds to the constant signal 1 1 1 1 1. So the z transform of the constant signal takes the form z over z minus 1. And as a direct consequence, for any constant alpha, the z transform of a constant signal is alpha times z over z minus 1. So in some sense the series, something that goes on forever, but we have a very compact, explicit representation of the series. And it will turn out that the root of the denominator of the series, so here the 1, will actually be critical, will actually capture what is the essence of the series. So let's look at exponential growth, for example. If in the series that we had before, instead of replacing z by 1 over z, we replace the z by 2 over z, then you see that the coefficients in those series, so in the z transform, they actually grow exponentially. So again, using the definition of the z transform, we see that this corresponds to the signal 1, 2, 4, 8, 16, etc., etc. So we have exponential growth. Now the z transform captures this very beautifully. So the z transform, so the capital X, is now z over z minus 2. And the root of the denominator is 2, is actually the growth rate. So the essence of the signal, so we have all these numbers that are growing and growing. So we have a very nice representation of this exponential growth series. And because this is so important, I have a second slide, so where we also capture exponential decay. So in our standard series, so the 1 minus z, we replace z by 1 over 2z to get the z transform. And now you see that we get exponential decay, and the root of the denominator gives us the decay rate. So in every step in our signal, we cut the signal in half. Okay, so I hope that this gives somehow an intuition of why the artificial definition of working with a series actually makes sense. So we can manipulate this. So let's see another property. Sometimes we delay a signal. So if we have an original signal x, x0, x1, x2, x3, with z transform capital X, so the big X, then consider the signal that comes with 1 unit delay. So what is now the z transform of the signal y? So what is the capital Y? Well, there is no y0, so we immediately start with y1, and the y1 is the x0 in the original system. So then there is no y1. The y1 here is now the x0, so the x0 is over z. Then the y2 is the x1. So you can see that we can write the z transform. So we work with the definition. And we see that the definition for y can be simply written in terms of the z transform of the original signal. So the delayed signal is the z to the power -1 times the z transform of the original signal. Okay, we are getting towards linear recursions. So why is this useful? We can capture a recursion relationship with this, but let me not run ahead. So delaying a signal is one of the techniques to make new signals. We can also start averaging. So we can take the delayed signal and add a weighted, so make a weighted combination of the original signal and then the delayed signal. What is the z transform of that new signal? Well, let's work with the definition. So here I worked with the big sigma, but if that big sigma is rather bit clumsy or perhaps a little bit too quickly, too abstract, let's, as an exercise, work this out with the ... operation. And if you understand it, say for the first 6 signals, you will see that it's essentially adding the original signal scaled by the factor alpha and then multiply the delayed signal via beta. So if also here this went a little bit too fast, an intermediate property is that if you take a multiple of a signal, then the z transform of that multiple is the multiple of the z transform. So the z transform of a multiple is a multiple of the z transform. If you add 2 signals, so the z transform of a sum is the sum of the z transforms. So I could have listed this as an exercise, but I hope you see that because of the property of the linear series, of the Laurent series, is that the z transform as an operation is a linear operation. So the z transform of a linear combination is a linear combination of the z transforms. Okay, You can use that property to write the first exercise. So we have a repetition, so 1, 2, 3, 1, 2, 3, 1, 2, 3. So we know what is the Z transform of 1, the Z transform of 2, the Z transform of 3. So you can combine them, and they are written with a delay and a repetition. So how do you combine the Z transforms? So that's the purpose of the exercise. Can you find a nice expression for the series? Okay, think substitution. So you can also make signals go faster or slower by inserting zeros in there. Okay, so perhaps I'm going a little bit too fast. So this is a lecture where I did not want to overcrowd with too many slides. So we will use Z transforms later. Let us go back to our original problem and see how that can lead to a recursion relationship. So here is our motivating problem again. We want to have an idea for the evolution of the number of riders on our train we will have. If at each station 40 people on average mount, and on average 4 out of 5 remain, or 1 out of 5 leaves. So at every station, so we start empty, so we have an initial condition. So we have a recursion relation that we would like to solve. So that is our mathematical model now. Xn is the number of riders in every station. So at the time 0, the depot is empty. At step 1, we will have 40. So in a way, we have always the constant 40. So the on average assumes a statistical solution. But let's now take these numbers 40 and 4 over 5 as exact numbers. So you can't really have 4 out of 5. You can't really have fractions of people, but it will turn out that the recursion relation will actually show something. Okay, so in general, we can solve recursions via the Z transform. First of all, what is a linear recursion? Well, we have fixed constants, and the previous recursion was actually a very simple one. We had actually only one. We had two constants. So here we consider a linear recursion as a linear combination of the previous n states. So the next state is determined by a weighted combination of the previous n states. Now, solving this recursion, so in a way this is a mathematics course. The course also follows both symbolic computation and numerical analysis. So in a way you could see this course as symbolic computation 2 and numerical analysis 2. But the focus is on problem solving and technical writing and mathematical modeling. So we do not see explicit, the focus is not on explicit algorithms, although here I hope to give somehow a flavor on how a computer might solve systematically a recursive relation, a recurrence relation like this. So, I mean, again, what matters in this course is that we can solve problems, and we will go to symbolic computation to solve it. So, there is a lot of mathematics here, and the course circles around a little bit. We will, if everything seems to be rather abstract and artificial, don't worry. I hope that it will become clear when we get more into system theory. All right, so this is the general principle on how a recursion relation is solved. Let's apply this to our motivating problem. So we will look at the z-transform of our recursion relation. So we have three terms. So the left-hand side is by definition. So the capital X is defined as the little x. Then we have the delay, so the xn minus 1, and then there is the constant. Perhaps I could start with the constant. So slides, they glide away, but we have seen that the constant signal 1, 1, 1, 1, 1 has the z-transform z over z minus 1. So we have the 40 in there, so for the constant alpha, we had alpha times z over z minus 1. We had the delay, and then we can apply also the linear product here. So we have the z-transform for our recursion, and we can obtain an explicit expression now for the z-transform of this process. Note that we are now doing something very magical. So with the data acquisition problem, we were assuming that we have given on input a signal. And with the z-transform, I said that we could capture growth or decay. So here we have described a problem, and we actually don't know really what is the input to our signal. So we could of course observe, and that would be indeed how you get to the 40 and how you get to the 4 over 5. But we don't really need to see simulation to determine the answer to the question, or one answer to our motivating problem. Okay, so let's not run ahead. So you see here that I have an expression for the z-transform. And the 4 over 5 is also one of the roots of the denominator. But it's kind of awkward. There's also the z minus 1 sitting there. So how can we solve this? Well, and here is where both symbolic computation and numerical analysis kind of convene. So the partial fraction decomposition is used in a symbolic integrator. If you ever wondered how a symbolic integrator works on fractions, well, it applies the partial fraction decomposition. So what, in some sense, this is a mathematics course. We're going to prove something. So if you're interested in mathematics, you might have been a little bit disappointed in the first 2 weeks, which were very much hands-on and practical. Here actually we have a theorem that says that if you have a quotient where the roots of where the denominator, so the denominator is a polynomial with mutually distinct roots. So we are not going into this specific case of any denominator. So we have some constants, and remember why is this relevant now for our problem. We had the -1 and the -4/5, or for alpha 1 we had 1, and for alpha 2 we had 4/5. So if the polynomial in the numerator has degree less than n, less than the degree of the denominator, then we can reformulate the quotient P over Q as a sum where we separate all the contributions from the denominators. So if you think now geometrically, so we are going to think mainly algebraically here, but geometrically, what does it mean to have a root in the denominator? It means you have an asymptote. And typically when you plot these things or when you work, you have to be actually careful. You may divide by 0. So most languages and most plotting environments are robust enough that your computer will not crash. But in some sense, you could also see geometrically what it does is that it separates all the problems. So if you're going to evaluate your rational expression now, you have to be careful if you get close to any of those roots of the denominator. So they are called the poles of the expression. Alright, if you took numerical analysis, then the condition of mutually distinct points may look familiar to you. So you may remember the interpolation problem. So for the interpolation problem, we also wrote it that way, that for the points with different indexes, there were different values. Here also you see in the expression at the right, it doesn't look that simpler, but we are having numbers. We have a sum of numbers. And these polynomials can have high degree. So in terms of evaluation, it's also actually easier. So we have a sum of 1 over x minuses. So you could also see this, you can see why this is also a problem interested in symbolic computation. So we are rewriting a fraction. Where does numerical analysis come in? Well, Lagrange interpolation. So in numerical analysis, we have seen Lagrange interpolation at several points. Here we see it again. So note that if you have not taken numerical analysis yet, don't worry. So this part is self-contained. But I hope that you can still appreciate the flavor. So an interpolating polynomial can be written as a sum of the function values at the point at which you are interpolating times functions that are on and off. So this product here, you can see that if x equals alpha I, then what we actually are computing is alpha I minus alpha j in the numerator, and in the denominator we always have alpha I minus alpha j. So when x equals alpha I, we actually have a product of ones. When x is not alpha I, then one of the numerators is 0. So the product here, it looks also a little bit daunting, but the product is 0, 1 function. We call it a Lagrange polynomial. It looks like complicated, but it's very, very convenient here. We will use this as a way to prove the partial fraction decomposition. That the degree of the numerator was less than the degree of the denominator is important. So if you think about a quadric, and we were having a denominator, degree 2, we had two alphas, then actually a quadric polynomial is entirely described by three coefficients. That's why p, if you have only two roots, you can only have degree at most 1. So that's why the numerator p has to have a degree less than 2 if you have only two alphas. What we started with, if you think about the interpolation problem, there is a unique solution. So the expression above is an identity. So the expression on this slide is an identity. And that is the key to the partial fraction decomposition. Because in what follows, we're going to rewrite this expression of the Lagrange polynomial. I'm going to multiply by 1, so this is 1 here, and I'm going to move it into the factor. You see now the j goes from 1 to n in the product cannot be I, but if I move in the x minus alpha I factor, so that's the missing factor in this product, then I have my q, and I can immediately already bring it to the left-hand side, divide by it. And what is left is the product of all the quotients, and now here you see that the condition that all the roots are distinct from each other is again very critical. So the derivatives are not 0 of q, so I can replace this by q prime. So I have my identity proven by Lagrange interpolation. Okay, where does this help us? So return to our motivating problem. So we found z transform, and we're going to rewrite this now so that we have the z minus 1 and the z minus 4/5 sitting in there. So the numerator, so with hindsight, I'm going to isolate the 40 out of z. So my p is z. So to make this easy, so if I evaluate at 1, I have 1. And I can tell you that the derivative is 1/5 in q, so I have the 5 sitting in there. Then I have the 4/5 when I evaluate at the other root at 4/5, so the alpha 2. So I can rewrite part of the z transform, and combining then, so I had isolated the 40 times z, and the partial fraction combination, then I find the z transform written as two components. So I have a component z minus 1, and I know z transforms are new, but remember the z transform of 1, 1, 1, 1, 1, 1, 1 is z over z minus 1. And I have that 200 sitting in there. So 200, I'm going to subtract something from it. And the 4/5 is also important, capturing the people that remain. So I find 200 as an upper bound. So I'm not going to do this formally by hand, so to speak, because we are using technology. But what I want to do with this z transform is indicate how powerful it is to extract critical information about your series. So we've seen the denominators are important, the 4/5 is important, but you see also that the constants come up, and the 200 will be part of our answer. All right. So, okay, so I'm moving along. So let's do symbolic computation. So we are using Julia in this course primarily. Julia has also an extensive ecosystem, but it also uses a lot from the Python ecosystem. So the computational ecosystem of Python is much more mature and established. And if you took MCS 320, you must have encountered SymPy. So SymPy has the very useful rsolve, which you may have encountered in MCS 320 to solve recurrence relations. If not, so then here is a very quick way how to solve this. And this also, it does not invalidate everything that I tried to explain before. I hope still that you appreciate the mathematical beauty and power of it. But if you ever have to solve a recurrence and you're in the field with your laptop, please use the software. Okay, so we're doing this here. And actually I'm going farther already, because in my symbolic solution I had not really used the initial condition. So I was not yet done there. But here I'm using SymPy. So again, if you're doing this for the first time, you may have to answer yes to install the package. So I will have to declare my symbols. So n will be used as the symbol, the independent variable in my recurrence. So n is the number of each station here in my motivating problem. I will solve for a function. So I have a symbolic function, call this x. And then I define my equation. You can also define an equation with the symbol equal. It will work, but then you have to be careful not to forget to switch the sign. So if you do minus 4 over 5, so the equation is written then as xn minus 4 over 5 times xn minus 1 minus 40. So here you're very closer to the symbolic way of looking at it. So the 4 over the 5 becomes the 0.8. That's the Julia thing, most likely. Then comes the formulation of the initial condition. So in Python, this is formulated as a dictionary. So here is where the documentation is often not so well done. So if you look at rsolve in the SymPy, you need to give the SymPy dictionary. But here in the interface, you have to give the equivalent dictionary in Julia. So here I defined it explicitly. So the dictionary in Julia is defined by the dict. So I'm indicating that at 0 there is nothing. So there are no writers. And then I can solve. I apply rsolve. I spend a lot of time on this, so you can see that it's very efficient if you know how to do this. And the number 200 pops up here again. So the number 200 we got from the Z transform already. Okay, so there will be a Jupyter notebook posted at the course website. Here you see the plot. The plot is also made with the Jupyter notebook. So in this solution here, we started at 0 and at 1 we have 40. And you see that the shape of the solution, after 20, our train actually gets pretty full. But it will be an ugly solution because you have pieces of people sitting there. So this is still an idealized model. So you have not really a good... So it is a mathematical model. So you can say, look, as a first answer, a first upper bound, you can say that this recurrence shows that if you have 200 seats, then you will actually accommodate your requirements. So here is our motivating problem solved. So you could see that the formulating of the recursion is a little bit our back of the envelope. So with 4 or 5 SymPy instructions. So the back of the envelope is what you scribble by hand, but this is already the 21st century. We actually don't use envelopes anymore to solve problems. We use computer algebra. So we actually found one potential solution. So that gives us a number to work with. So we have this number to work with, and here is then the alternative. So this goes back to the first week of classes, and again we are thinking now already upon our projects. So you can also, if you have not committed to a project, or if you think about a longer time problem, and if you're interested in public transportation, so I once took the train in the United Kingdom, and there things are privatized, so there is competition. So having to deal with disgruntled customers may cost you riders. So one could see this problem also from a careful logistical problem. This is an extra Monte Carlo simulation where here is where the simulation happens. Every rider, so the 40 comes up, and also here you could actually play with this average. So sometimes at some stops in certain simulations you can have that less than 40 people come up. So you can kind of work a little bit with more or less a deviation here. So how is that average being obtained? But first of all, work with exactly 40 in your simulation. And the simulation is here the coin toss. So everyone on board flips a coin. There are as many coin flips as there are riders, and 1 in 5 descends. So the thing about the solution here is that you will always have exact integers. So one run will give you a vector of 20 numbers. Now, of course, is the solution, then you average things out, and this is where the fractions come in again. So if you would make a plot, would the plot be similar to the plot we obtained by the recursion? So we are mainly concerned again with the number 200, because that's where, as a train manager, you have to make sure that your trains are long enough. Is that 200 a certain number? Or, I mean, and also your trains, you will probably, should you, so if you, so most likely it will not match. Should you then add an extra train, or should you remove one extra train? Suppose that you work, for example, with trains with 88 seats or something like that. Okay. The last exercise is an exercise in compound interest. So we can make now actually many mathematical exercises where we take any recursion, and the bottom line is rsolve will actually do it. So don't worry if the z-transform method looked extremely complicated. But the z-transform, I hope, gives you an insight into the magic of the symbolic computing systems. Okay, so I did not have over amount of material. So this was a balanced lecture. So this is the first lecture in a sequence of lectures on introducing the mathematics that is used in signal processing and systems theory. We will get far more in this. So we will mainly use this as a modeling tool. So here we used the recursion relations as an alternative to the Monte Carlo simulation. So in solving problems, one method will definitely be useful, but it's typically that more approaches are definitely needed to look at the same problem. With that, I close.